in a non-conductive environment. We can say there is an electric field in this space between the plates. And we can say that there is a potential difference phi since to move a test charge from the right plate to the left plate. And the relationship between the charge on each plate or Q and the potential differences that exist between them is called capacity. The capacity we can write as C equals to Q divided by V. And then the value of the capacity of this structure, which we call a capacitor, depends on its dimension and shape. In this case, the geometry of the figure is the capacity is given by C equals to epsilon null, and then A divided by D. D is the distance for the distance, and A is the area, to area of the this plate. And this expression is valid if the plates are in a vacuum and are infinitely large. If there is a material between them or the electric, the capacity is greater. So we can compute as C equals to epsilon null dot epsilon r and dot A divided by D. And the constant epsilon r is the relative dielectric constant in vacuum of the material between the capacitor plates. This increased capacity is due to the molecular polarization of the electric in certain material, such as water. The molecules have a permanent dipole, while in others, it required an electric field to create the poles. Uh, in any case, the molecules of the material tend to align with the direction of the electric field, or we can call it the electric polarization. Okay, it's the electric polarization. And in the left figure, the molecules are randomly aligned, while in the right figure, they are more or less aligned according to the applied electric field. This electric field caused by the charge present on the capacitor plates. Uh, but you have to note, due to the thermal agitation and molecular organization of the material, the molecules in the latter case are not perfectly aligned with this field. The positive side of dipoles is facing the plates that has a negative electrical charge in the right plate, and the dipoles having an electric charge can give rise to an electric field. Uh, Given that the electric field has the orientation of positive charge to negative charge, the field created by the dipoles of of the electric or uh, A, or not A, but E, is opposed to the field created by the charge in the capacitor or epsilon null plates. And the resulting field or E is therefore smaller than the field that we would have if there were no dielectric E null. If the plates were in a vacuum, weaker electric fields lead to a lower voltage between the plates. Okay. So this is the resulting field, and this is the dipoles of the electricity, the electric. So the voltage that was phi null in a vacuum becomes phi equals to phi null divided by epsilon r. Inserting to this into the leads, C equals to epsilon null Q divided by V null equals to epsilon R dot C null, where the C null is the capacity value in a capacitor without the electric. And this is how you get the expression C equals to epsilon null epsilon R A divided by T in the previous slide. In short, the presence of the electric decreases the voltage for the same charge. It means with a dielectric, it is possible to have more charge with the same voltage that is greater capacity. And we can read the value of the electric constant of the different materials. Notice the compound of the thick film capacitor, which is made especially for the capacitor and which reach the electric constant 5,000 times greater than that of vacuum. And the other material typically used in capacitor, such as ceramics capacitor, and also presented in this table. This is the material, and this is the value of the electric constant. The electric constants of a material depends on the temperature and operating frequency. Determine agitation of the electric molecules due to an increases temperature will affect the alignment of their dipoles. The dependence on frequency is since the dipoles must reorient themselves in each period of the applied voltage because the applied electric field inverts this, uh, their direction. Different crystalline structure of the electric make that reorientation easier or more difficult. Ideally, to make a capacitor, the electric constant does not vary very much with frequency, as is the case of polyethylene is desirable. And the capacitor can have many different forms. The most typical shape are flat plate. Uh, it is given by C in the previous slide. We know that C equals to epsilon null and dot epsilon r a divided by d, and the circular plates as the illustrated uh, in this figure for the cylindrical capacitor, and in a good capacitor the the electric constant and the geometry must be stable based on this equation for the plates capacitor. C equals to 2p dot epsilon null dot epsilon r 1 multi divided by L and B divided by A, where is where L is the length of the capacitor plates and A is the inner plate's radius and B is the outer plate radius. Ideally, uh, the capacitor should not vary with temperature, humidity, pressure, or any other environmental factor. Good capacitors are fundamental components of electronic circuit. However, to create sensors, it is desirable to have a bad capacitor. For example, a capacitor whose capacity varies considerable with the physical parameter that is measuring. In order to build a sensor that is based on the capacity effect or the capacitive effect, it is only necessary to look at the analytical expression that determines your capacity. In this case, of the plane capacitor, whose the capacity is this, this is the value. It's possible to build a sensor if the physical quantity to measure can cause a change in C equals to epsilon dot A divided by D plus 2W divided by P epsilon ln PW divided by D. Note that the expression of the capacity of a capacitor is an approximation used for condensers with infinite plates. And in the real case, where's the length of the flat conductor is W. And the second term leads in the final sensor to a nonlinearity that may, however, be greatly reduced using quartz electrodes that completely involve the capacitor plates, as will be seen later. In the following, some example, some example of the sensor that use capacitive effect uh, are addressed. This is the example of electric actuators and MEMS actuator or electrostatic comb drive. COM drive are used in many MEMS applications such as resonators, micro engines, and gyroscope. The force generated is low, usually less than 50 micro coulomb. However, these devices are predictable and reliable, making them usable for variety of the micro application. So if we previous talk about the mechanical actuators, that the actuators can be seen, use our eyes, and these MEMS is kind of actuator too, but the size is very uh, tiny, tiny. But this is still a kind of actuator that used in IC or integrated circuit. And this image is an example of MEMS, electrostatic drive resonator, which is a common MEMS actuator. So, or maybe you have known that nanotechnology, it's kind of the part of electronics knowledge that creates integrated circuit using nanomaterial, yeah, in size. Okay, in size. So this is like in kind of that. Uh, a resonator is a device which naturally oscillates at its resonance frequency. The oscillates no, but in nanotechnology it's just different in size, but this is micro, in size is micro. So okay, we continue. The resonator in here make oscillation, can either be electrostatic or mechanical. As an actuator, this COM drive resonator can move another object at the rate of the COM drive oscillation. In the introduction to actuator, we will study a microelectromechanical system that use COM drive to move optical mirror. This is the MEMS that uh, the implementation on resonator. So this is the electrostatic MEMS actuator explanation. The electrostatics actuator use the electric field to create a force between two conductive parts, a fixed and a moving one. So this is the moving part. The MEMS actuator is to create a force, okay, force in here, the force between two conductive parts, and it is possible to create electrostatic actuators within an integrated circuit made of silicon. The application of a voltage between two electrodes causes the attraction of opposite charge due to the Coulomb force. The value of the exerted force can be calculated as any mechanical system by varying the energy stored in the system to displacement caused by the force F equals to uh, this is called alpha, okay, or delta, sorry, delta W divided by delta X, and where X is the direction in which the COM is free to move, and energy in a condenser is given by W equals to half dot C dot P square, and the force is therefore proportional to the square of the voltage and to the derivative of the capacity in relation to X. We can compute as F equals to half dot delta C divided by delta X dot V square. Given the expression for the capacity of a plate capacitor as a function, its geometry, we will recall again that C equals to epsilon null dot epsilon R A dot A divided by D. We have in the case of COM actuator, like the one illustrated in this figure, the force is equals to N and epsilon null H divided by G V square. And where N in here is the number of teeth of the cam. So in mechanical on actuator like here, the teeth is like mountain and slope, but in the MEMP actuator, uh, this is the teeth. Oh, sorry, this is the teeth. Uh, this is an approximately uh, value because this expression is only accurate in the case of plate capacitor within an infinite area. So the force that acts even each tooth of the comb with a height equal to its spacing or G, with height H equals to its spacing. For 15 volt voltage is around 10 to 9 amp. It is found that the smaller the distance between the teeth, the greater the force that created. On the force is proportional to the square of the applied voltage between the fixed comb and the movable comb. We have to remain that the force doesn't depend on the displacement x. That is, the force is always the same throughout the travel of the movable comb. And in this case of the gap closing for this actuator, where is the displacement of one plate is the direction of the other plates in the previous slide. Uh, so the force is given by F equals to or close to an epsilon null h divided by 2x square dot phi square. And the force in this case is not the same throughout the path of the plate. It's closer they are, the greater the force is. Okay, this is for the MEMS and implementation that use MEMS. Uh, One of them is for gyroscope. Gyroscope is for the angular velocity sensor. This is the illustration of constitution of vibrating gyroscope with a single test. They measure the velocity and this is the actuator and this is the anchor and this is the vibration axis and this is for the test mass. Gyroscope is a sensor that measures angular velocity in radian per second. This is a three-dimensional vector that contains information about the axis of orientation as well as the speed of rotation. And the gyroscope is one of sensors that used in our smartphone. Okay, accelerometer, gyro, and the wide implementation is on robotics. Okay, there are two types of gyroscope: rotary, which is based on conservation of angular movement, and vibration, which are based on conservation of linear momentum. The first one have a mass continuous rotation or a wheel, whose axis of rotation is independent of the orientation of the sensor. The second has a mass in continuous vibration whose direction of vibration is independent of the orientation of the sensor. The second type is the most commonly found in customer electronic devices because they can be built using integrated circuit manufacturing techniques and MEMS with the consequent decrease in production costs. It is the second type that will now be covered in the detail. A vibrating gyroscope has one or more test masks that are vibrated by an actuator. So this is the actuator that make a movement. The test mass thus performs a periodic linear movement. The test mass of thus performs this can use springs because in practice uh, two test meshes are used instead of one to double the sensitivity and make the response more linear. This is the illustration of the constitution of a vibrating gyros gyroscope where the test mass and part of the sensor frame are visible. Uh, okay, this is the test mass and this is the spring and this is sensor frame part and this is the vibration axis for the two or more test mass. And also show that the sensor frame between the test masses and the frame. There are springs that serve to balance the friction force that appears when the sensor rotates. Okay, this is the use, uh, the reason why in this gyroscope is used springs. And this is the illustration of the relative position of the sensor and the vibration axis of the test mass when the sensor rotates about the yaw axis. In the yaw axis, there's three axes for X, yaw, and Z. The inertia determines that the test mass, keep their movement always along to the same straight line or axis of vibration. If the sensor rotates in a different orientation as this picture or this figure, the vibration axis of the test mass remains or momentarily in the same place. As noted, the distance between the packets and the test masses has changed. In the case of the test mass on the left, so the distance has increases. And in the case of the test mass on the right, this distance decrease. This distance measured indirectly by measuring the capacity of the flat capacitor whose armature are attached to the frame and the task masses as in done in the accelerometer already covered. So this is the capacitor plate for spring. This is for the extended spring, and this is for the compressed spring. If the sensor rotates a certain amount and then stop, the test masses due to the spring that connect them to the package will reposition themselves parallel to the package as they were initially. This sensor is not, however, an orientation sensor, but an angular velocity. If the package uh, is in constant rotation, there will always be a different distance between the rest masses and the package. It is this distance that are measured that determine the angular velocity. So, in the previous slide, a rotation of the sensor around the yaw axis has been illustrated. The measurement of the capacitance of the represented capacitor make it possible to determine the yaw component of the angular velocity. And two other test mass with a vibration axis along yaw and another pair of capacitor and restitution springs are used to measure the component according to A. So this is the illustration for the measurement of the component according to Z of the angular velocity. The same test mass are used as in the case of measurement of the component according to yaw or measures to vibrate along the x-axis. But the displacement between the test masses and the frame occurs along the yaw axis and is measured by capacitor, whose armatures are perpendicular to the axis. As we show in this figure, this is the test mass and this is the actuator. There are a flat capacitor between the frame and the test masses, and to measure the Z component of the angular velocity. And there are sensors in the market with a range from 250 per second on or plus minus 500 degree per second and plus minus 2000 degree per second with measurement frequencies from 100 hertz to 800 hertz. Its size is extremely small, within 4 millimeters on the side and 1.1 millimeters in height. So this is for the gyroscope. And next, we will talk about electric actuator based on magnetic field. It is one of cleanest and readily available form of the actuating system, as it doesn't not involve oil, such as on the pneumatic actuator, for example, as there's no need to compress air or in hydraulic or in the pneumatic, so it's no extra machinery, electrical. In electrical energy is always available on ship. The electrical energy is used to actuate a mechanical system using magnetic field. For example, electrical motor, DC or AC motors to operate a valve and magnetic valve actuator or solenoid valve. An electrical, I'm sorry, An electrical actuator is powered by a motor that converts electrical energy into mechanical torque. The electrical energy is used to actuate equipment such as multi-turn valves. Additionally, a brake is typically installed above the motor to prevent the media from opening a valve. If no brake is installed, the actuator will uncover the open valve and rotate it back to its closed position. If this continues to happen, the motor and actuator will eventually become a damage. So, for example, in plant of oil and gas, uh, the electrical actuator is one of the cleanest and most readily available form of the actuator because it does not directly involve oil or other fossil fuel. So this is the diagram for the electrical actuator. They need this is the actuator actually. This is the motor uh, uh, to make something move. So if we want the motor is rotate, we need a controller, and controller will connect it to the driver, and the driver will generate the motor to rotate. So this is our material.